Good and welcome to video 2 in the series Insightful Integration. In this problem here, you need to understand separation of variables and how it works. It's a differential equation that looks a little bit different to your NCA ones, but I assure you that you don't need any university maths or any maths beyond the curriculum. In NCA, differential equations come in one of two types. Either they're separable or they're written in a form where you just anti-differentiate them. So this is one of those two types. All the best, and we'll see you on the other side for the solution.
Okay, so this differential equation looks a little bit strange, but I can assure you it's actually a pretty standard one. The thing that makes it look messy is the notation. We've got the operator d dx on the right hand side, which just means the derivative with respect to x. The weird thing is it's the derivative of the square root of y with respect to x. So implicit differentiation needs to be understood. The other thing is that it's quite subtle, but in the problem itself it underlines the word all. And what that means is that you've got to be careful that you get all of the solutions. And if you just go about doing calculus and not thinking about it, you might end up missing a solution. And what I mean by that is if you were solving, say, x squared equals 2x, if we solve that and we just cancel off an x on both sides and get x equals 2, we've lost the solution, the trivial solution of x equals 0. And the better way of solving this, of course, is to factor, and then we get x equals 0 and 2. So be careful as we're working our way through this to make sure that we get all of the solutions. Okay, I'm going to actually start there. The tricky one, the one that you might not spot, is a trivial solution, and it's a constant. Okay, if y is a constant, if y equals, say, k, a constant, the dE is satisfied. Okay, so that one there is just by inspection. I've looked at the problem and I've got the square root of the derivative of a constant, dy dx. Well, if y is k, dy dx is equal to 0. And then the right hand side, the derivative with respect to x of the square root of that constant, that's also going to be 0. Okay, so it works, and therefore y equals k is our first potential solution, just a constant. Okay, now if we look at this problem, and the first thing I want to do is to square both sides, but squaring the left-hand side's okay, I can just get dy dx, but squaring the right-hand side's a bit strange because I've got to first up differentiate this square root y thing. So first up, I'll do that right-hand side's root dy dx equals the derivative with respect to x of y to the half. Okay, so if we think about this, d dx of y to the half, that's something to the power of a half. This something could be sine x, it could be, we don't know because we're trying to find that, but it's something, some function of x to the power of a half. And so when I differentiate that, I get a half something to the minus a half multiplied by the derivative of the something. Okay, that's all chain rulers. Like for example, if it was sine x to the half, I'd be differentiating that as a half sine x to the minus a half, and then I'd be multiplying by the derivative of sine x. And so that's why when we use implicit differentiation, we have a dy dx factor at the end of it. Okay, the second thing is now we can square both sides. We've got dy dx equals a quarter y to the minus 1. Squaring a half is a quarter. Squaring y to the minus a half, y to the minus half times itself will give you y to the minus 1. And then dy dx all squared. You've got to be careful that you don't write it as d squared y over dx squared, because there's the second derivative, and what we're not getting the second derivative, we're just getting the first derivative squared. Okay, Now that's kind of similar to the quadratic I gave you earlier, where I said you've got to be careful you don't cancel solutions. Because if I just cancel off a dy dx on both sides, let's change the colours to make it look a bit easier. If I do that, I've lost dy dx equals 0. And dy dx equals 0 is y equals a constant. So we got that solution earlier by inspection, but it actually appears in our working here, and it might have been something we missed if we'd not been careful with the algebra. I can cancel it now that I've recognised it's a potential candidate. Now I've got 1 equals a quarter y to the minus 1 times dy dx, and this is just a separable differential equation. So if I separate both sides of the equation, I've got 1 dx equals, actually let's take the 4 up there as well. I find it a bit weird having dx on its own, so put 4 dx up there, and then we're integrating 1 over y, or y to the negative 1, dy. Put an integral on both sides, and it's just an achieved problem now. The integral of 4 with respect to x, 4x. The integral of 1 over y is ln absolute value of y, and then we need a constant somewhere, so let's just put it here, plus c. And when making y the subject of this, it's a pretty standard rearrangement. Actually, let's put the plus c on the other side, just so that the rearrange it's a little bit tidier, and then go take the e of both sides, e to the 4x plus c. You would have seen these before in your calc class, because we can write this as e to the 4x multiplied by e to the c, and then we just changed e to the c to be another constant. So we've got the absolute value of y is equal to a e to the 4x. And I can get rid of the absolute value symbols there, because all that's saying is that it's the y value could be plus or minus, and that can be absorbed in the constant. So we could say something like y equals b e to the 4x, where b is some constant we need to work out. And we don't have enough information because the problem doesn't give us any initial conditions like a coordinate that the function goes through. So we've got two possible solutions: either y is equal to k, a constant, or y is equal to this exponential function here. Hopefully you found that useful, and we'll catch you in the next video.